today we're going to have a look at recursive subroutines. Now, I don't want you to worry or panic over recursion. Recursion is simply, our recursive function is simply one that calls itself. So we know how to call subroutines from subroutines, and so recursion just means that we're going to call the same subroutine from itself. You probably know this already, but I'd like to go over it in just a little bit of detail before we get started. So let's have a look at an example of a recursive definition. So we're going to use the classic example of the factorial. Now, of course, factorial for a number n, as written as n exclamation mark, meaning n factorial, is simply n times all of the numbers less than it. So n times n minus 1 times n minus 2 times everything down to 1. And this lends itself well to a simple recursive definition. Now over here, I have a definition of factorial using Haskell sort of notation here, where the factorial for n is defined as being equal to n times the factorial of n minus 1. And then the base case, which is what we should be working our way down towards, is says that factorial of 1 is just equal to 1. So this will allow us to get n times all of the numbers less than it, and then when we get down to the position of 1, it'll just go, oh, okay, 1, that's the base case, we're done. So let's have a look at how that evaluates when you actually call it. So for factorial of 5, the first substitution you would make is 5 times the factorial of 4. That's the n times n minus 1 part. And then you do 5 times 4 times factorial of 3, so you just evaluate factorial of 4. And then you keep doing this. There's a lot of intermediate steps that I'm too lazy to go through, but then we get 5 times 4 times 3 times 2, and then we get to the base case, and it's just a 1, which ends our evaluation there, and we return the result. So this is a fairly simple definition of the factorial. We're going to put it into MIPS. As I say, don't worry about recursion too much. It's more straightforward than you would imagine. But let's have a look at how we do it. So, first things first. We're going to call a subroutine. So we are going to need a stack frame at least. And in fact, in the way that we're going to structure this, we're going to need 2 stack frames. So I'm going to start off by making them. So let's add immediate onto SP. The value of -8. Now remember, a stack goes down the way, so by adding on -8, I'm actually making it larger because I'm pulling it down. So this creates 2 stack frames. Now, when we create a stack frame, or when we have a subroutine which calls another subroutine, the first thing that we want to store is the return address, because we know that the jump and link instruction will overwrite whatever is stored in RA. So we need to make sure we have that saved so that we can return to wherever we were originally in code. So what I'm going to do is I'm going to do store word. It's going to be RA, and we're going to store that at SP. And that means save return address for later. So when we get to the end of this, we're going to need to pull that back from memory so that we can jump back to that position. So what should we store next? Well, the way that I'm going to structure this is we're going to get down to the bottom, as in we're going to get down to our base case of 1 before we actually do any of the multiplication. So what I'm going to store there is A0, because A0 will likely be manipulated by this subroutine. I mean, I happen to know that that's what's going to happen, but you have no guarantee that A0 is not going to be manipulated or overwritten by the subroutine. So I'm going to store that at the stack pointer as well. I'm going to put that at 4. So save original A0. Okay, so that's most of the initial, the first bit done. So what I then want to do is implement my base case, because I don't really want it to have to run through the whole function, do a recursive call, or well, I don't want it to do any recursive calls if we've reached the base case, so I'm going to check that first. So what I'm going to do is say branch greater than, and if A0 is bigger than 1, I'm going to jump to a part of the code that I'm going to call large. So check for base case. Now if it's less than or equal to 1, then I'll just fall through this branching instruction. So now I need to implement the behavior of the base case, in which case I'm going to load into v0 1. So this is base case. Happy days. And then I should jump to the end, which I've not defined yet. But this is just saying, well, you can probably imagine that the jump to end is going to be something like jump register to RA, destroy stack frames, load values back, all the stuff we would do at the end of a subroutine which has a stack call in it. So that's as implemented this little bit of code up here, essentially. And now we need to figure out how to do this bit. And we're going to kind of do it in an opposite way round, well, at least it might seem an opposite way around. But what we're going to do is we're going to do large here. And what I'm going to do immediately is add onto a0 the value of -1. So this goes, n goes to n minus 1. Okay, so now we want to call the subroutine with that value. So I'm going to jump and link to Factorial. So this is the recursive call. And so I'm feeding that the value of n minus 1 because that's what we should be calling on. We should be moving towards the base case rather than running away from it. Of course, here we're not checking to see if we have any negative numbers. Don't really care about that for now. This is assuming we get a positive number in. So what should we do next? Well, in this case, what we've done is we've called the recursive function. So it should do this bit of the sort of calculation here, all of this, because it should be going down towards 1. And when it comes back up, it should have the result of all of that stored in v0. So we need to do this part 5 times. Now, we need to get our original value of a0 back. So I'm going to load into a0, because after this, we get back to this line 26 here. That'll mean the Factorial recursive call has already executed, so we don't need to worry about overwriting the value there anymore. So this is why I structured it. You might think it's the wrong way around to do the n minus 1 before the multiplication, but that's why I'm doing it this way, so that the recursive call can get a value of a0, and we don't need to worry about overwriting it. So I'm going to load from stack pointer, now I put this at 4 of SP, so get original n, and now that I have that, I can do the factorial part, where I do mult v0 of a0. And this is n factorial. So, well, this statement isn't, but when we get to this point it will be equivalent to that, because what we've done is we've essentially just called this function over and over again. Eventually it will get to this part here where it loads a value of 1 in, and then it will start to go back up the recursive call. So you could think of it as like the first call is taking a step down, n minus 1, then n minus 2, then n minus 3, and then it multiplies back up to the top. So when we have this, we've actually done most of the heavy lifting. So you can see it's not actually that complex, it's just you need to think in a slightly different way. But let's do end. Now I need to go back to doing everything, or undoing everything that I did at the start. So I need to load word into array from the stack pointer. So get original return. Then I need to destroy my stack frames. So I'm going to add on to SP, value of 8. So this is destroy stack frames. And then I want to jump register to RA. And that's just handback control to caller. Or caller, if I could say it right. So that's our recursive definition. Now I don't want you to worry about recursion. Recursion seems like a complex concept, and it can be, but really you just need to think of it as calling your own function that you've written. So you just need to structure it in a way such that you automate all of the heavy lifting yourself. So let's run this and see what happens. This is just code to put in a value of 5 and then do the printing. So this should return a value of 120 because it's 5 times 4, which is 20, times 3, which is 60, times 2, which is 120, times 1. So let's assemble this and run it. And there we go, 120. Now, again, I don't want you to worry about recursion. We'll be doing some of it in the labs. I think the labs are the best time for you to do the trickiest stuff because you can quite easily come and speak to me or Xenon for help. So I wouldn't worry too much about it. It's good that you get practice in an environment where you can get support. So when you see the lab exercises, don't panic because you're asked to do recursion. Just fire into it and come to me if you have any questions. But thanks for watching this video. I hope you found it useful, and I'll speak to you later.